Yeah, this script is going to talking about the unit load method that we are going to use to analyze the frame for the frame deflection. You may review back to what we have in the analysis of thrust and beam that we use the unit load method. In the unit method, that's we just mentioned the name of it is called the method of virtual work. Okay, virtual work, and it can be used to analyze the thrust, to analyze the beam, and to analyze the frame. This is the third type of structure that we are going to use this method of virtual work. We also can call this as the unit load method. Okay, many people call it by unit load method because when we analyze structure, we will put the unit load, maybe unit force, maybe the unit moment into the point of the structure that you like to determine the deflection or the slope. Okay, and the principle of this is based on the same concept as you know before, the external virtual work must be equal to the internal virtual work. By doing this, we're going to consider the work. When we consider the work is the force times the displacement or the moment times the slope. So we're going to consider the first one. Always we consider the elastic curve of the structure. That's I mean maybe for the thrust, maybe for the beam, and maybe for the frame. Okay, and formulate. Oh, sorry, I should skip this because I need somewhere here to write something and formulate. Okay, and formulate the okay virtual work equation. Actually, we have the virtual work equation here already. Okay, but need more explanation to review it. Under the first, okay, this is fixed. This is fixed. When this is fixed, okay, V sub C H equal to V sub C V and equal to zeta sub A and equal to 0. And then you may imagine that under this force, this is the rigid connection. Under this force, this point A supposed to move to somewhere here. Okay, let's call this A part. Okay, by moving that, this frame gonna have some deflection. Okay, and the deflection supposed to corresponding to what we have the support here. So this beam will deflect like this, and for this portion it should deflect like this, and the structure gonna have this kind of deformation. And since this one is the rigid joist, before this is has the okay normal angle between the beam and the column. So later that this one also be in the normal angle. Okay, and what we have is this is going to be the vertical deflection. This is going to vertical displacement. We call this V sub A, V at point A, V. And it also has this one is the V at A H. H, horizontal direction. And the last one is the slope. This is gonna be zeta sub A. Each point of the beam, each point of the frame gonna have three. Okay, three. Yeah, it's called degree of freedom. Okay, which is the horizontal, vertical, and slope. And also this one. Okay, this is the known displacement at a joint. Okay, we call this is as geometric boundary condition. We call it boundary condition. It's geometric boundary condition. It's boundary condition about deformation. Okay, and since the frame have small, very small deformation. Okay, and then so the beam and column of the frame of the frame will have very small axial displacement. So it will not elongate or contraction per se. Okay, it's going to be have the same length, same length. When you have the same length, if you know this horizontal, okay, horizontal displacement at A, you also will know this horizontal displacement as B, and they are going to be equal. The beam will not elongate or shortening, and no shortening of the column. So displacement at B in vertical direction gonna be 0. We know this. This is the boundary condition that we know. And the last one, the rotation. The rotation. The rotation. If you have this and this is similar, and you put this, and you have this, and then you put this. So the rotation here. Okay, from this one to this one, from this one to this one, that is counterclockwise rotation, zeta sub b, gonna have some value. So there are some deformation, this diffraction, and slope. That's we need to determine if you like to find the real shape of this frame. But usually we didn't need to do so. We just used to solve for some problem, something. So if you like to determine, okay, for this deflection at A, and let me call it in short of delta A. Okay, what we have is we're going to have this frame, and then we're going to put the 1.0 force to this is 1.0 kilonewton here. Then this 1.0 kilonewton times this displacement is gonna be the external virtual work, and then this is going to be internal virtual work. This is going to produce m, let's say m sub delta. Okay, and this is going to be equal to integration of m sub delta, and this m sub delta is produced by the assumed unit force. It's going to have the change in the slope of the frame. So it's mass times the zeta. And as you may know, we have the deflection, we have the dv by dx equal to slope, okay, and then we have d square v by dx square equal to curvature. And now we may rewrite this one by d by dx and what? And you may put this one for for dv by dx, and that is going to equal to m over ei. And what we have is going to be the d theta. This is going to be d theta equal to m over ei and dx. And then you put this is going to be m over ei and dx. You got this portion by putting this delta to recognize for is the moment due to the unit load over here, used to determine the v sub a in vertical direction or delta a. Okay, and then if you determine the slope, you got to have the same thing, but this time your frame gonna be subjected to its slope, right? Slope is the rotation. So to produce the work, you got to put the 1.0 kilonewton meter to this. Got to put this, and this one 1.0 gonna time with this theta sub a, and this is gonna produce the external virtual work. And again, this is gonna produce m sub theta, and this m sub theta again, gonna produce the internal virtual work. So this is gonna be equal to integrate m sub theta. However, the change of the slope still here. Okay, this is for the capital M. The change of slope still here. That means you put m over ei and dx again, and then you got this. Just put this one, okay, and then you get this. So the procedure, the second procedure, after you got this, the second procedure, you got to find what? M and m delta m theta equation. Just find their equation. To find this equation, you got to put very important thing is you got to set up the coordinate. You got to set up the coordinate. For this one, you may set this one is an x1, and this one is for the x2. And if you set this one for the x1, x2, this one also have this one for the x1, this one for the x2. They all the same in the same direction. Also, if you set the moment here, if you cut here and have the force here, you get this one for capital M1. And then you cut this one for free body diagram of the 1 unit load. This is going to be m sub delta 1. The direction of the moment here and direction of the moment here, they must be the same also. So every time you set up the coordinate, every time you set up the direction of the moment, just make them the same. Okay? Okay. So you start the analysis of this second one to find m, and then you find small m, and the later part we put this one as the 3. We compute the design deflection or slope by using the virtual work equation. That's all the required step that we are going to have it. It's very simple 3 steps. But you got to work on many problems, to use your knowledge, to gain your skill. Okay? Okay, if you understand that, let us start by very simple problem first. This is steel frame, the same thing as we considered before. It's cantilever steel frame and has the E, has a section of 360. This section is going to be the the W Y frank section with this one about 360, the depth. and actually the width also about is 360 millimeter, and it's going to be 64 kilonewton per meter. Each meter gonna weight like your guys, okay? And they asked us to determine the vertical, horizontal displacement and the slope. So the basis that we just talking about can be used here. Now, let us start by determining the vertical displacement. What we have is we're going to have the same one at this, which is going to be interested at A, okay, in the vertical direction, okay. Put 1.0 here. So under the force, this one gonna defect something like this, okay, and this is going to be delta A, okay, you times 1.0 kilonewton. With delta A, you get the external virtual work, and then this one going to produce M, capital M, this one going to produce small m, and since the force act at the same point with the same direction, so this small m gonna be capital M divided by 10. Okay, by doing this, just find the capital M and set up all the coordinates x1 and x2 here, and you may say this one 0 less than or equal to x1, x1 or equal to 3 meter. The same thing, 0 less than or equal to x2, x2 less than equal to 3 meter. That is the length for this coordinate, and then we cut this here. By doing this, you take the moment here, you have the summation of moment equal to 0. So the m1 plus 10x1 equal to 0, the same direction of this, and then the m1 going to be minus 10x1. For the m2, this one you take the moment here, okay, summation of moment equal to 0. So this m2 is going to be in the same direction as this one. This is m2 plus, but this one gonna time this moment arm. This is 3 meter, 30 equal to 0. So m2 is going to be minus 30 kilonewton meter. That's for the capital M. It's going to be used for finding the horizontal displacement, vertical displacement, and the slope. So, like I said, the small m is going to be 10 times less than the capital M, due to the force here is just 1 kilonewton compared to 10 kilonewton. So we have the table. Okay, if you like to do, put them on the table and do the integration like this. Putting on the table, I mentioned this one, x1. We have mentioned about this already. This is constant I, and then we're going to have this guy together, minus times minus is going to be plus. And for the x2, the same integration 0 to 3, and using only I, and integration of the 90 plus 90. Okay, and then put them together. This one gonna be what? 10x1 square. So 10x1 over 3 by 3 EI from 0 to 3. And this one is 90, so it's 90x2 divided by EI from 0 to 3. So this one going to be 270. Okay, and this one going to be 90. So it's going to be 90 plus 270. You got it for 360. And since the value is plus, okay, so the direction gonna follow the unit load. That's we said is downward, like this. And then you put into your equation, and don't forget about changing the unit. And then you get this for 10 millimeter. Okay, that makes sense. Very small deformation. That is vertical direction of 10 millimeter. Okay, and next we're going to find the horizontal displacement. The capital M stays the same, but now we put the one unit, okay, at the A, and then when you cut the element by basis on the given coordinate x1 and x2. You may have the first one, this one will point along the axis. So if you do the summation of moment equal to 0, this is going to be 0. Okay, and this one, the next one, the line of force is going to be here. And this is going to be the moment arm. If you take the moment summation of moment over here, you may have m sub h2 gonna equal to 1 times x2. This is going to be equal to x2. Okay, that's positive, right? And then now the capital M you know already. You just put into the table, and you can see that the first integration over here is 0. Okay, that means no effect of this 10 kilonewton on the deflection, on the displacement, on the horizontal displacement of number AB. And we have only this. So the integration is going to be very simple. Only one part. This part is 0. So this one is minus 30 x2 integration square over 2 and 0 to 3. This is going to times EI. Okay, this is going to be 15 and this is going to be 9. So this is going to be minus 15 times 9. Minus 135 divided by EI. Minus is mean what? It means the direction that you push the 1.0 that you put in this direction is wrong. Okay, so actually it's in the opposite direction. Okay, it's going to put on the left. That is going to be 3.8 millimeter, not in opposite direction of this. And you may get this one like this. That is going to be 3.8 millimeter. And you may find the total resultant deflection here. Okay, the resultant delta at A equal to square root of 10 square plus 3.8 square. That is going to be the vector of the moment from here to here. Okay, this is going to be the resultant of this. Just put them into the calculator. You got this in millimeter. Okay, that is going to be 3.8 square, 14.44, and then plus 100. Okay, and then you got to take it by a square root. It's going to be 10.697, 10.7. This is about 10.7 millimeter. Okay, and it's have this one, and you may have the angle here if you like. So then if you have the tangent here, okay, with reference to the horizontal line here, that is going to be the theta A. Next, we determine the theta A. Okay, we do theta A, and then we put the equation that we have here. The 1 unit gonna time the theta A, but this time what we have is the theta A gonna do to the moment of 1 unit here, and then this one gonna time theta A. It's going to produce the external virtual work, and then this one gonna produce m sub theta. You just cut by using the x1 and x2. And then if you summation of moment equal to 0, take the moment here, this is going to be positive. So they move in the same direction. So this one is going to be minus 1. And this one also. The next one, if you cut it here, okay, and you set this m sub theta 2, so summation moment equal to 0, and you may have m sub theta 2 equal to 1. Minus 1, sorry, because it's going to the same direction and move to the left hand side of the equal sign is minus 1. And then you put them together and do the integration. You get the rotation. And if you put the EI into it, the rotation gonna have unit in radian. Okay, the rotation gonna have the unit in radian. And finally, you got this for what? 0.003773, like this. And now you have what? You have this is theta A. Okay, this is deflection at point A, horizontal. Deflection at point A, vertical. And now the deflection at point C, horizontal, equal deflection at point C, vertical, equal to theta sub C equal to 0. That is boundary condition. And since the beam have no axial deformation such the same as the column, so what we have is this one, V sub BH is going to be 3.8 millimeter. And see over here also, V sub BV is going to be 0. Okay, and this is rigid joint, this is perpendicular, this is going to be in perpendicular. If you reference it with this, this is going to be theta sub B. You can determine it, okay, by what? Putting the 1 unit moment at B, and then you will get the result of this. Okay, that is the end of this clips, and you guys, I will have some more demonstration to solving for the slope and for the horizontal and vertical displacement of the frame, okay, in the next clip. For this one, let me finish the clips here. Okay.